Hello and welcome to Empowered Learning. This video will be about antiderivatives. And so when we talk about antiderivatives, what we're really just saying is that we want to take a derivative backwards. So if we're given some function, then we want to find out where did that actually come from. And so what I mean by that is this. Let's say we have some function and that function is a derivative of something else. We want to know what that something else is. Okay, so that's what antiderivatives are all about. In your study in calculus of antiderivatives, one of the things that you're going to find out is that doing the antiderivative operation is what allows you to be able to get formulas for the area under the curve of a particular function in between some closed interval of x values. And so calculating an antiderivative or evaluating a particular function for its antiderivative is a skill that we need in order to be able to study the area under the curve of a function, because depending on some applications, there is some meaning of the area under the curve of a function. And so we won't focus a lot on the actual meaning of that. We'll just focus on actually calculating the antiderivative. One application of calculating antiderivatives and we'll actually see this towards the end of this particular presentation, is if we have information about something in terms of its velocity or its acceleration, then we can figure out a formula for its position function or its distance function based upon that information. And of course we know that because the derivative of position is velocity and the derivative of velocity is acceleration. Okay. All right, so the verbiage that I have here just is talking about basically how we have the limit operator in calculus, or the derivative operator in calculus. Doing an antiderivative is also another operation. Okay, and so this particular operation just basically undoes a derivative. And so we need to look at taking antiderivatives in that way. It's like an operation. There's a lot of things that are involved in that one step that we don't necessarily say, we just do it. Kind of like how when we talk about the limit of a function, there is a lot going on with that, but we just simplify it to the limit and we sort of build our foundation and then just operate on a higher level. Same thing with a derivative. So we know that a derivative is just the limit of the difference quotient, but we don't go and say that every time now that we know that our differentiation rules. So again, just want to give you some perspective on what we are talking about and what we're doing whenever we talk about antiderivatives. So our definition for an antiderivative is real simple. So here we have, if a function, and I'll just call this big F, is called an antiderivative of little f on an interval I if the derivative of big F is equal to little f for all values of x that are within this particular interval that we're talking about. And so to give a real concrete example here, so let's consider our little f function to be 4x cubed. And of course, if we play around a bit, we'll find out that x to the fourth is actually the antiderivative of 4, is an antiderivative, I should say, of 4x cubed, because if we take the derivative of x to the fourth, we see that we get 4x cubed. Okay. Now, the reason why I said that x raised to the 4 is an antiderivative is because antiderivatives aren't necessarily unique in all cases. And so if we look here, we see that if we were to add a constant to x raised to the fourth, then if we took the derivative of that, we will still end up with 4 times x raised to the 3. So what we notice here is that x to the fourth is not the only antiderivative of 4x cubed. Matter of fact, 4 x raised to the 4 plus any constant x raised to the 4 plus any constant would be the antiderivative for 4 times x raised to the 3, or 4x cubed. So in this instance, we know that whenever we find antiderivatives without any what we call limits of integration, or put another way, we basically defined and said, hey, we're trying to find an antiderivative, but we're not specifying in between a set of x values, then we call that the most general antiderivative. And so I have this note here, and this basically comes from courses that I teach. And there is a basic fact that comes after the mean value theorem that basically says if you have two functions that have the same derivative, and that is true for all values of x within some interval here, then we know that these functions only differ by a constant. So we're just saying here f of x will be equal to g of x plus some constant. And so what we are referring to back here with saying that x to the 4th plus c is the most general antiderivative of 4x cubed is that here if we had two functions that basically had the same derivative here, then that means that their antiderivatives are only different by a constant. So to make my point, we have x to the 4 plus 2, let that be f of x, and let g of x be x raised to the 4 minus 5. Of course, if we take the derivative of both of these, they're going to be equal to one another, which is just going to be 4x cubed. Okay? And thus, if we had these two functions together, if we subtracted them, then of course this difference would be a constant. So this is what this is saying. F of x minus g of x, the difference only in that would be some constant. So if I took f of x and subtracted it from g of x, then here I would have a difference of just the 2 minus a negative 5, okay, which would end up being a positive 7. So that's what this note is talking about. So now for our most general antiderivative, of course we're going to call that big F again. If big F is an antiderivative of little f on some x value interval I, then the most general antiderivative of little f on this interval is going to be called big F of x plus c. And so I've just sort of given you a concrete example of this. And this is going to be our alternative notation for saying that we want to take an antiderivative. And so you'll see later on in your study in calculus that this particular symbol here is going to be like an infinite sum. But we're going to borrow this because we know that whenever we do this, this is also talking about the area under the curve of a function. So, and to get that, we're going to have to take antiderivatives to do that. So we're just going to employ this notation now, but we're going to see where it actually comes from later. All right, so here's some basic antiderivatives that we can use. So, of course, this first one here, we're just saying if we have some function and we want to take the antiderivative of it, we're basically ignoring the constants. If for the second one here, if we have the sum or difference of two functions and we need to take the antiderivative, we just take the antiderivative of each and then add or subtract those answers. Okay, now for the rest of these, most of these will seem familiar because, again, we're just doing the derivative backwards. But this is the one thing that is sort of new. And so we'll see here that x raised to the n, where n is not equal to 1, then in this case, what we will do is add 1 to the exponent and then take that whole result and divide by that. And so essentially what we're doing is the derivative backwards. So of course, if I had x raised to the n and I took the derivative of it, I would be multiplying my function by n and then subtracting 1. But now what we're doing is the reverse of that. We're undoing what we have done. So in this sense, if I'm taking the antiderivative of it, then instead of multiplying first, I am going to do adding first. So I'm adding first, and then instead of multiplying here, I'm dividing. So we're just undoing what was done, okay? And if I was to take this in particular and say I want to do the antiderivative of this, then of course this would look as follows. I would add 1 to this and then divide by that. And you'll see here once I'm done, in my numerator here, I just have x raised to the n, and in my denominator, since that cancels, I would just have 1, which gets me back to here. So you can see how the antiderivative just undoes whatever our derivative is. Now, for the rest of these, this should be familiar to you if you're at this point in calculus. The antiderivative of 1 over x is just natural log of x, and of course I'm putting the absolute value signs here to adjust for the fact that I may be able to plug in negative numbers in some instances. But we know that 1 over x is the antiderivative of natural log of x because natural log of x, its derivative is 1 over x. Of course, we know that e to the x is a derivative of itself, so its antiderivative will also be that way as well. The derivative of sine is cosine, so therefore the antiderivative of cosine is sine. And here we know that for negative cosine, if we took the derivative of that, that would be positive sine. So the antiderivative of sine is negative cosine. And so I'm not going to go through all of these one by one, but you just kind of see how for this general list, how whatever we know the derivative of some function is, if we want to do the antiderivative, we just go backwards. So now what I want to do is go ahead and get started with some examples. All right, so the first thing that we want to do is find the most general antiderivative for this function f of u. And for here, to make this easier for ourselves, we want to split this up into 2 separate fractions here. So we want to do u to the 4th divided by u squared plus 3 times u raised to the 1/2 over u squared. And so I've just changed the square root of u to the 1/2. Now for the first term, that just simplifies to u squared. For the second term, we know that we can subtract the exponents per our exponential rules. And so here I'm changing 2 to be 4 divided by 2. And so now we know that 1 minus 4 is negative 3. And so this is what we have. U squared plus 3 u raised to the negative 3/2. So now what we're going to do is take the antiderivative of that. Okay. And so this time I'm not going to use this infinite sum notation for here. I'm just going to do it. So if we know that f of u is this, then of course the antiderivative would be big F of u, and this will be u raised to the 2 plus 1 divided by 2 plus 1 plus, we ignore the constant, and then we do u raised to the negative 3/2 and plus 1, but I'm going to write 1 as 2 over 2 since I have a fraction, and I'm going to divide that by negative 3/2 plus 2 over 2. And then of course at the end here I put the plus c, and I have to have the plus c at the end to show that I have the most general antiderivative. If you don't put the plus c there, then your answer is incorrect. So here we know that 2 plus 1 is 3, so this just ends up being 1/3 u cubed. And in our denominator here we have a negative 1/2, and this will be 3 raised to the u negative 1/2. So we have 1/3 u cubed, and of course when we have negative 1/2 in the denominator, this is like saying 1 over negative 1/2, which is the reciprocal of negative 1/2, which would be a negative 2. So we have negative 2 times 3u raised to the 1/2 plus c there. And I forgot to put my plus c here, so let me go ahead and stick it in. And now to finish up, we just have u divided by 3, or 1/3 u cubed, minus 6u raised to the negative 1/2 plus c. And I'm going to finish up by putting everything back in root form. So that would be 1/3 u cubed minus 6 divided by square root of u plus c. And this would be the most general antiderivative for this. All right, so let's move on to our next example. All right, so for this next example, I've already worked it out. And we see here that we have our function 5x raised to the 4th minus 2x raised to the 5. And we have these initial conditions here. And so basically what this says is that we have the point 1,4 on our graph. So now I'm using this notation here. And again, I just didn't do it in the last problem because you really don't have to. Okay. The only time that you have to use this infinite sum type notation is when we start to do integrals, or if you check out my video on definite integrals, you'll see that we need to use it then. But here we're just asked to find the most general antiderivative. So we need to find the antiderivative of 5x raised to the 4. And you see how I'm adding 1 to the exponent and then dividing by the exponent there. We ignore the 2. And then we do the same thing. Add 1 to the exponent here and then divide by that. And then do the plus c. And so from there you see how I've done my simplification to get to this point here. And so this is what my big f of x is. Okay. So that's what we state right here. And so from that point, since we're given this initial condition, basically saying we have the point 1,4 on the graph of this function here, then we allow this to be x, allow that to be y, and we plug those things or evaluate our function with those values, and we just solve for c. And so therefore, once we plug everything in and work it out, we see that our c ends up being 10/3. And so we just allow that to be c. And then by looking at this, what we realize is that we know that little f of x was derivative of many functions. And of course, this was the many functions that it could be the derivative of. But by saying, well, out of those many functions that could fit the description for being an antiderivative for this function here, we wanted to pick the specific one that had the point 1,4 on its graph, because there's only one that will do that. And so that's why we had to solve for c here. All right, so now let us find the most general original function for each of the following. And so we're going to go ahead and go with a here. And notice that I have a second derivative. So this means that I'm going to have to do the antiderivative process twice. So first, I'm going to find out the first derivative, and I'm actually going to use this notation now by doing the antiderivative of what I see here. And if I do that, it's going to be 6x 1 plus 1 divided by 1 plus 1 plus 12x raised to the 2 plus 1 divided by 2 plus 1. And then that's going to be with c. So from there, that's just 6x squared divided by 2, 12x cubed divided by 3 plus c. And that just ends up being 3x squared plus 4x cubed plus c. And so that will be our first derivative. Now for our original function, we need to take the antiderivative of what we just found. and we'll do the process over again. So that will be 3 times x raised to the 2 plus 1 over 2 plus 1 plus 4 times x raised to the 3 plus 1 over 3 plus 1. And whenever we take the antiderivative of a constant, that's just going to be that constant times x. Because again, if we took a constant times x and we took the derivative of it, we would just get that constant. Like if we said the derivative of 2x, that's just 2. So if we go backwards, if we say what is the antiderivative of 2, it'll just be 2x. So that's why we have the c times x here. And then, of course, since we're taking an antiderivative, we need another constant. So I'm just going to call that constant d. You can call these constants anything you want. I'm just calling them d. And so now from there, we know that 2 plus 1 is 3. So this and this will reduce to 1. 3 plus 1 is 4. So this and this will reduce to 1. And we just have x cubed plus x to the 4th plus cx plus d. And that will be our most general original function for a. Now looking at b, we see that we have sort of the same thing here. We start off with our second derivative, and we go ahead and work that out. And we see that the first derivative is just the antiderivative of the second derivative. Plug that in, and then of course we add 1 to the exponent and divide by that. Clean everything up and make it look nice. And we see that that is our first derivative. From that point, we take our first derivative and take the antiderivative of that. And of course, again, we're adding 1 to the exponent again, but making 1 look like 3 over 3 since we have a fractional exponent. Dividing by such, cleaning everything up here. And then once we clean it up, of course, we know that we had to add the extra constant here because we were doing a new antiderivative. And we see that the antiderivative of c is just cx. So we got to remember that. And once we clean everything up, that's what the answer is. So let's move on to some other examples. So for here we have an example of we need to find out what f of t is, but we're given some initial conditions. And so if you notice here, since we have the second derivative, we know that when we find our original function, we're going to have 2 constants. And so since we have 2 constants, we'll call them c and d here. That means we have 2 unknowns. And if we have 2 unknowns, in order to figure out what those unknowns are, you need at least 2 equations. And so by us having this these initial conditions here, we essentially have the 2 equations that we need. And so this just effectively says I have the point 0, 0 on the graph and the point pi 0 on the graph. So let's go and find the first derivative. And we're going to do that by finding the antiderivative of 2e raised to the t plus 3 sine t. And if we do that, we know that e to the t, its antiderivative is itself. So we just repeat 2 times e to the t there. The antiderivative of sine is going to be negative cosine. So we would have here negative 3 cosine of t. And then, of course, we would have the plus c at the end. So now we need to find the original function, which is going to be the antiderivative of the first derivative, which will just be the antiderivative of what we just found. And here, again, the 2e raised to the t is antiderivative of itself. We know that the antiderivative of cosine is just sine because the derivative of sine is cosine. The derivative of any constant is just that constant times the variable, which in this case is t. And then we have plus our other constant d there. So now that we have this information, we're going to use what we know here. Evaluate the function at 0, let it equal 0, and see what one of our constants are. So having this, of course, x here is 0, y is 0, or I should say t in this case. So let me get rid of that. Use the correct variables here. So this is t and y. T and y. So here we know that 2e raised to the 0 minus 3 sine of 0 plus c times 0 plus d is going to equal 0. And since all that equals 0, and e raised to the 0 is 1, what we're going to have is 2 plus d is equal to 0, which implies that d is equal to negative 2. So we know what one of our constants are. When we have f of pi is equal to 0, we do the same thing. Here we have 2e raised to the pi minus 3 cosine of pi plus c of pi. And then, of course, we know d is a negative 2, and that would equal 0 there. And if we work this out, we know that cosine of pi is going to be, let's see, because of course cosine looks like this, right? And so pi is right there. So cosine of pi is going to be a negative 1. And here we just have c of pi there. So this is 2e raised to the pi plus 3. And then this would be what's this? Yeah, just c pi minus 2 equals 0. Yeah, I think I made a mistake here. I should have had sine, not cosine here. So I'm going to erase all this and start this over. So at least get rid of this part. So this should be sine of pi, and that should be 0. And so that means all this will change as well. Yep, so sorry about that, y'all. And so we're here, and that's 0. Then this will just be plus c pi minus 2. And then from there, we can finish this up. So this would be, if we were trying to solve for this, 2e raised to the pi minus 2. We'll subtract c pi from both sides. And then we would need to divide both sides by negative pi. So from that point, you could leave it like that, or you can factor out the negative, or actually negative 2. And if you did that, you would just have 1 minus e raised to the pi over negative pi. And of course, a negative divided by a negative is a positive. So that would be your constant there. So our final answer here would be f of t, and that would be equal to 2e raised to the t minus 3 sine of t plus our constant c here, which would be 1 plus e raised to the pi, all that pi t, and then plus our constant negative 2. So this would be our final answer here. All right, let's move on to the next example. All right, so for this example, we have a particle that is moving with the given data. And so that given data here is we have the acceleration of the particle modeled as a sum of sine and cosine functions. And we also know that the position function, s of t, we know when t is equal to 0, that means the position is 0. So that means it's at rest at that moment. And we also know that at a time of 2 pi, the position is 12. So just like how we did in the last problem, we know that if we take the antiderivative, we're going to actually find the first derivative of position here. So we know that acceleration is going to be the second derivative of position, and we know that velocity is going to be the first derivative of position. So when we find the velocity here, what we're actually finding is the first derivative of position, whereas this is the second derivative of position. And so, of course, we substitute what a of t is. The antiderivative of sine is negative cosine. Antiderivative of cosine is sine. And then, of course, we append the plus c at the end. Clean everything up. And here is what our velocity is, our first derivative of position. If we move on to our actual position function, we have to take the antiderivative of the velocity, or antiderivative of the first position, of the first derivative of position. And so in doing that, scroll down here, we see that the antiderivative of cosine is sine, and the antiderivative of sine is negative cosine. And the antiderivative of a constant is just that constant times t. And then, of course, we have to append our constant at the end of that antiderivative. And then we clean everything up, and we see that our position function is just negative 10 sine of t minus 3 cosine t plus ct plus d. And so now we use our initial conditions here to be able to figure out what our constants are. So here, when t is equal to 0 and y is equal to 0, or s is equal to 0 rather, I should really say s here, then we just plug in 0, or evaluate our functions here at 0, and we see that the only constant that we have left here is this negative 3 in one of the terms, and just d itself, so we know that d is equal to 3. And similarly, when we evaluate our function at 2 pi, we know that we're going to get 12, and so sine of 2 pi is 0, cosine of 2 pi is 1, and of course we just stick 2 pi right here. And once we get through simplifying and rearranging everything to solve for c, we see that c ends up being 6 divided by pi. So our final answer here just ends up being negative 10 sine t minus 3 cosine of t. And of course our constant c here is 6 divided by pi t, and our constant here is 3. And so this will conclude the presentation on antiderivatives. Hope this helps, and if you need me to do any more, or if you have some special requests, then just let me know. Take care.